It could be my computer, it might be yours. I hope it's not mine, because then the video is not going to look very good when we have it recorded. But, hopefully it fixes itself. I know we had an issue, it might have been this class yesterday or on Monday. Yeah, so Devin, you're seeing it too. Let me turn off my video for a second, turn it back on, because I know that that kind of fixed things the last time.
How do we talk on this? Can you hear me?
I can hear you right now, Vale. Yep.
Okay.
You're currently unmuted.
I'm still trying to figure this out.
So there is a button that can mute you. Well, let's see if, does that help the screen a little bit? I'm getting a head shake from William though. Oh, let me pause for a second. All right, so now that we've got our technical difficulties fixed, let's get back to this. So in terms of x-intercepts, the most that you're going to get is n. It's actually equal to the degree of the polynomial, but you could have any number. All right, so the maximum number is n, but it can go down. Okay, in terms of how many minimum you have, it depends on the degree again. So for the min is 0 if n is even. So just like with the range, there's a difference if it's even or odd. So if you have an even degree polynomial, it's actually possible to have no x-intercepts. But for sure, you're going to have at least one if n is odd. So every odd degree polynomial will have a intercept, an x-intercept, but even degree polynomials, it totally depends. It depends. You might actually end up getting 0 depending upon how things shake out. So yeah, going to generic polynomials makes a lot of this stuff a little bit more difficult, but there are definitely patterns to this. There are definitely patterns, and it all comes down to even and odd. That's the most important thing with polynomials, actually, if you're going to try to determine features about them, is seeing if they're even or odd. So a couple more things that are of interest when it comes to polynomials. Let me put up end behavior. So what I mean by end behavior is what's happening as we go towards infinity, either plus or minus. And again, it depends on whether you're even or odd. So I'm actually going to make 4 different pictures here for the corresponding possibilities. Okay, so up here we're going to have n is even, and the second column is going to be n is odd. But just because n is even, that's not enough to tell us. We also need to look at that leading coefficient. And so it depends on if that leading coefficient is positive or negative. So here's what's going to happen in these 4 cases. For the evens, if that leading coefficient is positive, as we go towards infinity or we go towards negative infinity, this graph blows up. So what I'm going to do is basically just put a little box here. That box is whatever's going on in the middle of the graph. I don't really know. It could be just a strict parabola. It might be doing some sort of waviness. I don't really know, but I know at the ends, that's going to go up as I go to the right and left. If n is even, but it's a negative leading coefficient, then on either end, it's actually going to drop down. again, think about my happy parabolas, sad parabolas. Use parabolas as your generic case, or your, sorry, not your generic, your specific example of the generic n is even. Think about what happens at the ends of those. That's what happens at the ends of even degree polynomials. So similarly, if n is odd, we can think of an odd degree polynomial as an example. So think about a line. If that leading coefficient is positive, that would mean its slope is positive. Then what we're going to see on the ends is like a positively sloped line. Again, weird stuff can be happening in the middle, but at the ends, it goes up as we go towards positive infinity, and it goes down as we go towards negative infinity. Well, same thing happens here. It just gets flipped. So we've got n behavior doing this. So when I teach this in pre-calc, this is usually when I show you the polynomial dance. Basically, your arms. So it's a little bit tough because I've got a smaller screen now. But the odd degree positive a sub n does your, it doesn't do justice on the small one. Basically, I start doing my John Travolta, is what I'm saying, right? So think about John Travolta in Saturday Night Fever. He's doing the polynomial dance, depending upon what degree and all that. Anyway, but these are all the different cases. Every polynomial does one of these four things. Which one? Well, just match it up to even, odd degree, positive or negatively in coefficient. All right, so again, we know a lot about these. And then the last thing I want to mention about polynomials that can come in handy and will come in real handy for us at the end of Math 105, and that is the turning points. So I call these turning points. You can think of them as like the little hills and the troughs and stuff, because like when you draw a polynomial, right, you get things that look like this. What you can tell me actually right now is that you know that this is an odd degree polynomial. He says confidently. Why should you be able to tell me that this is an odd degree polynomial?
Opposite direction ending points.
Yeah, look at the ending going in opposite directions, and they're going up to the right and down to the left. So that was the odd. You also know the leading coefficient is positive, right? So, but when I talk about turning points, I'm talking about these locations. Look at those four dots. We've got two little hills, two crests, and two troughs, two valleys, something like that. So this one would have four turning points. So think about a quadratic has one turning point. A line has no turning points, right? So you can imagine all kinds of different polynomials having a different number of turning points. Well, the number of turning points is also determined by your degree. So the maximum number the actual name for these turning points, I might as well mention it now because we'll see them later. They're called extrema. It's the plural of extreme. So this would have four extrema. But anyway, so the maximum number of turning points is actually equal to n minus 1. So at most, you can have one under your degree. So think about then a quadratic. Quadratic is degree 2. So if we take 2 minus 1, that gives us 1. That tells us that there's at most one turning point for a quadratic. Well, yeah, we know that. We know there's always a turning point for a quadratic. Think about a line. N is equal to 1. 1 minus 1 is 0. So lines cannot have any turning points. Well, yeah, We already knew that, right? Lines never turn around. But what's kind of interesting about these is not only do we know a max, we know a little bit more, because turning points always come in pairs. So think about this. If I eliminated, say, this first max here, this first maximum, this first hill, so we don't have that anymore. Well, if there's no turning point there, then we lose this min at the same time. These two would go away together, or these two would go away together, or those two. So every maximum and minimum, if you put one in, you have to put in the other. So not only do we have a maximum, but we also know that the only possible options are this minus even number. All right, so basically we can have this many, or we can have n minus 1 minus your favorite even number. So I know that this is probably really confusing the way that I've written it. As I'm listening to myself talk, I'm going, oh my God, this makes no sense whatsoever. Let me show you an example, and then I think it's pretty clear. So let's say that we've got, for example, degree 7. So we've got a polynomial that's x to the 7th. In terms of the possible number of turning points of extrema, we could have at most 6, right? We can have 1 under our degree, so there might be 6 of them. But I could also take away even numbers. So I could take away 2. So it might be that this has 4 extrema. I could take off another 2. So I might have 2. Or I could take off another 2 and actually have 0. So if I have a 7th degree polynomial, I will have either 6, 4, 2, or 0 turning points. I will never have an odd number of turning points for this one. Similarly, let's go with an even degree. We've got degree 6, just to make life easy. So in terms of the number of extrema, the most I could have is 5, but then I could also have 3, or I could have 1. I'm just taking away 2 every time. So 6th degree polynomial, I'm guaranteed to have a turning point. I'm going to have at least 1. But I could also have 3, or I could have 5. So when we get to that section, it's in, I think, maybe chapter 4, maybe the end of chapter 3. We're going to be looking at trying to draw graphs of functions without technology. And when they're polynomials, this is one of the things that we're going to use. We're going to definitely keep track of how many turning points we might have, because that will help us when it comes time to actually drawing the graph. And after we do a little calculus, I'll bring this back when we start talking about extrema, and you'll see why the most is n minus 1. Because right now that probably feels a little magical. When you took pre-calc and someone was like, oh yeah, it's 1 less than the degree, you just kind of smiled and nodded because that was the best you could do. Well, I'm going to give you the tools this quarter where you can see why that is. That's how much power you're going to have by the time you're done with calculus. You're going to be able to prove all this stuff that you did in pre-calc and you sort of just took for granted.
I have a question.
All right. Well, anyway, so yeah, go for it.
Well, if we're like an engineering student, like, wouldn't we be able to do all this on like MATLAB or other software and not have to show all the work eventually?
So obviously I can't answer that because I'm not an engineering teacher and I was never an engineering student. I've never taken a single engineering class in my life. So I can't answer exactly what technology you have to do all the different things, and if you're actually going to have to do any of this on your own. So I can't answer that. Now, obviously, when we do things in math, there are lots of things you learn how to do that you don't necessarily need to know how to do because there is technology to do it. Like, for example, if I ask you what's 5 plus 7,
12.
you know the answer, right? The answer is 12. Do you need to know that?
No. Or
No,
maybe.
because I mean, you could crack out your phone and do 5 plus 7, and it will tell you 12. Now, I can see on your face you're kind of chuckling. Why are you kind of chuckling at that example?
Because someone would learn how to do that at a younger age than college, for the most part.
Okay. Okay, but if we're going to talk about learning things, you learn them when you get there.
Yeah,
right?
I would learn how to do it, but I'm just saying, like, eventually, from this process of calculus, how much would we actually need to input into a system?
Yeah. Well, again, I can't answer that, but my argument always to the, well, we got technology that can deal with this sort of stuff is I go to that example of like 5 plus 7, and most people are like, well, no, I wouldn't even bother the calculator because it's super fast. I just know 5 plus 7 is 12, right? And that's kind of where you'll get with calculus. You'll get to the point where it's faster for you to do the calculus by hand than to try to input it into technology.
Except for Newton's law of cooling. I don't know how that would be faster by hand.
Well, it depends what you're trying to do with it. Like Newton's law of cooling, the hardest part is getting it set up, right?
Yeah.
Right. So, and obviously it depends, but I will tell you that for lots of the stuff in calculus, when you get good at it, when you've done it a lot, obviously I have, 30 plus years of experience with calculus, but when you get to that point, it's super fast just to do it. And like you can outrace people putting it into technology, but there are definitely times when you do go to technology. So it's a balance. And
Okay.
I can tell you, like my son is a physics major at UNR, at University of Nevada, Reno. And there are some of his professors get mad at him for showing too much math because he's also, he thinks he's going to be a math major too. But he'll get in trouble with his physics teachers for doing too much math.
That's ridiculous.
Which makes me laugh, yeah. So,
but thank you. Thank you for
you're
your
welcome.
Can I ask a quick question as well?
Yeah, absolutely. Was that you, Leah?
Yeah.
Okay, cool.
Can you just talk about why the difference between even and odd in end behavior? Like why even and odd specifically?
Just in general with polynomials? Okay, so yeah, I'm going to come on the screen a little bit here. I'm tired of talking off of it. So even and odd seems like a real random, why is it that evens do one thing and odds do another, and even and odd are really it's the differentiating factor for lots of different things, right? Like you saw for end behavior, for number of turnaround points, and all kinds of things. So I'm going to give you the answer that everybody loves. There are two answers I can give you. The one is because. I'll never give you that answer because there's always a reason, right? But the second best answer that everybody loves, and I'm saying love sarcastically because nobody loves this, is, oh, you'll see, right? I'm gonna defer this one to the future, but not very far, not very far. I promise you, we will see this in probably a week and a half, maybe, probably sometime next week. I will be able to show you why it is that even versus odd is a big differential when it comes to polynomials. It actually has everything to do with the first thing we learn in calculus, which is called the derivative. And when we learn how to find the derivative of polynomials, you'll see how that also then depends on even and odd and how this whole even odd swap matters. So I apologize sort of for the kicking it down the road, but it really kind of needs to. And I promise you'll go, oh, this makes total sense why all this other stuff happens. But it is kind of an interesting thing, though, about polynomials, that every time you kick it up a degree, you completely change the fundamental structure, but it's related to the structure of the one that was one lower, right? So yeah, it's a little bit weird. Anyway, I don't know if that makes you satisfied or not, but that's the best I'm going to give you right now. So
Great, thank you.
yeah, you're welcome. Any other questions about polynomials before we talk about some other important structures? No, we're good? Okay. So next one on our list are absolute values. So these are the ones that just look like f of x is equal to the absolute value of x. So this is another one that when you see it, you should immediately be able to picture it in your mind. And I don't know if you guys can. Are you at that point? Anyone know what this looks like?
Yeah, like a Y, the top of a Y from the origin.
Okay, so the top of
It's
the
a
Y,
V.
I love this. Most people just go to call it a V, but yeah, we'll take top of a Y. It's all good. So it looks a little bit like this, right? So you include the bottom of the y-axis, it definitely looks like a Y. But there's your absolute value of x, right? So it looks like this. In terms of its domain and its range, domain is anything. You can plug anything you want in. Its range is just non-negatives, right? You can get anything you want out that's from 0 on up. You get 0 out when you plug in 0, and anything else, absolute values give you the positive. Because what absolute value really does is just find the distance from that number to 0. And if we're talking about distances, distances are never negative. That's why the range is what it is. All right, so there's its domain and its range. And in terms of the intercepts, it only has the one. The origin is both an x-intercept and a y-intercept. And it is the only x-intercept. All right, so it sounds like we're all pretty good with that one, absolute value of x. All right. The next one is I want to talk about a radical function. And there are a bunch of these, but for the most part, they're based off of the square root of x. So radical function, square root function is specific, but there are a bunch, right? There's the cube root, the fourth root, the fifth root, there's all kinds of things like that. But let's just specifically look at the square root. The other ones, I don't expect that you know. This one I expect you know what it looks like and how it behaves. Let me hold up here a second. So as you said, for the polynomial, to find the first 0, do we use the PQ method? I'm assuming for PQ, you're talking about you look at the factors of the leading coefficient and then the constant, and you make the fractions. So I call that the rational root theorem. That's how I learned it. You can use that to help you try to find them, but they don't always show up that way, because that only happens if the roots, if the zeros are rational numbers, but they may not be rational numbers. They might be things like square roots and other weirdness, but you can use that to help you try to find the roots for sure, if it's nice. So what I recommend, it actually depends on the situation. What I recommend is, well, let's say we got no technology. So you got nothing. You don't have a calculator, computer. So you're really just trying to, plug through it on your own. I definitely recommend that as the first step, the one you call the PQ method. I look for rational roots and I try to see if any of them work, because if I find one, then I can basically divide it out, lower the degree of my polynomial by 1, and it gets me closer to finding all of the roots. If I can't find one, I use what we call the intermediate value theorem. And basically that's find a number that when you plug it in gives you positive. Find another number that when you plug it in gives you a negative. And then what you know is that there is a root that's somewhere in between those two. And then you can kind of, whittle yourself down and make that gap smaller and smaller and smaller. It's really time intensive and it really kind of sucks. But that's one way you can get there if you don't have technology. If you've got your technology with you, and like I mentioned last time, I go everywhere with my TI-89. I always have my TI-89 with me, so then I can just like draw a graph. I can use that to visualize where the intercepts are, and that can help me narrow it down faster, or just hit solve or something like that. But really, if you're searching for roots, it kind of depends on the context, which method to use. But yeah, I think that's about as good an answer as I'm going to give you right now. All right, you're welcome. Okay, so let's get back to radical function. For this one, this graph looks a little bit like that. Square root of x, I like to call it a drunk parabola. You can also call it a sleepy parabola or whatever, but it's a parabola that's on its side, or at least half of a parabola that's on its side. I'm going to draw some, don't draw this part. Don't draw this part. I'm just going to draw a little dashed guy down here, right? This would be the other half of the parabola. So you can see the parabola on its side. Why do I not include that dash part? Why did I tell you not to draw it?
Because it's a radical function, and radicals are 2.
Yeah, it's the function is that key word again, right? Remember the function, you can't get two different y values. If I've got a parabola on its side, it fails the horizontal line, or sorry, vertical line test. So when we talk about square roots, it's only positive values. So this is what this guy looks like in terms of its domain and range. They're both 0 to infinity, including 0. So you can put in any non-negative number you want into the radical, and you can get out any non-negative number you want. So it looks a little bit like this. So you already know about, you can't put negatives in there, because when you put negatives in there, you get complex numbers. So that's pretty easy to remember. The domain is 0 to infinity, but the range is the same. Notice that it, just like with the absolute value function, has one x-intercept and one y-intercept, and it's at the origin, right? So I'm just going to recycle that since it's right next door. But this one, unlike the absolute value function, this one is always increasing. So it's an increasing function, right? It goes up as we go to the right. It definitely starts to flatten out, but it keeps going up. Just goes up slowly. So it is an increasing function. I didn't mention this with absolute value. We'll back up to it in a second. But radical function, notice that it's not even. It's also not odd. It doesn't have either of those symmetries. But absolute value is. Absolute value function, which one is that? Even or odd?
It would be odd.
Even.
Wait.
Uh-oh.
Yeah.
We're going to have a fight.
Even because it's both, no, because it's both going up on absolute value.
So remember the two kinds of symmetry. There's the reflect over the y-axis, and there was that rotational, right? So this one does not have the rotational. Rotational is the odd symmetry. The mirror image over the y-axis, that's even symmetry. So absolute value is actually an even function. So square root is neither. Some radical functions actually are. If this was an odd index, if it was a cube root or a fifth root or a seventh root or something like that, then it actually is an odd function. It does have that symmetry. You'd see the same kind of picture, but down below. But plain old square root is neither even nor odd. And square root is the only radical function I expect you to be able to draw like that, not even think about. Okay, so don't worry about the other ones like the cube root, the fourth root, and so on. When we run into them, we'll investigate them further, but this one should be able to come up quickly from the recesses of your brain. All right, so there's the radical function. Next one I want to show you is an example of a rational function. So rational, if you haven't picked this up in your math experience so far, rational just means fraction. Anytime you see the word rational, it means fraction. So rational functions are ones that are made of fractions. And the only one that I expect that you know is 1 over x. Okay, there are all kinds of other rational functions, but they're all kind of related to this one in a way. Okay, but 1 over x is the most basic of these. And what this one looks like is it's actually a hyperbola. I don't know if you remember hyperbolas, but this is a hyperbola. And its graph looks something like this. In terms of its domain and range, the domain is everything but 0. We can't put in 0. That gives us division by 0, which you know is one of the ultimate sins in math. So the domain is everything but 0. And it turns out that the range is similarly everything but 0. You can't plug 0 in, you can't get 0 out. Everything else, you can't. It also has no intercepts. And it's not very often that we find functions that don't have any intercepts whatsoever, but this is definitely one of them. So this guy is 1 over x. Now, every other rational function, rational again just means it's a fraction of polynomials, has some sort of variation of this. As soon as you start messing around with it, you might get intercepts, you might change the domain and range a little bit. But there are some features of this graph that are always present in every rational function. The first is vertical asymptotes. You notice this has a vertical asymptote at the y-axis. Asymptote is just a line that you approach. So you think about this as a wall. As we're driving towards it, we got to turn so we don't hit the wall. Well, that's a vertical asymptote. There's also a horizontal asymptote at the x-axis. Similar kind of deal. All right, so there's your rational function. I do need to give you a little bit more of my terminology because I don't call this one. You won't hear me reference it as a rational function or as 1 over x. I actually call this the butterfly function. So this is Bruce speak. Okay, there may be other people that say this, but not that I know of. I call this one the butterfly function. And if you can't see why, now you can. Right? It's the wings of a butterfly. So if you ever hear me say butterfly function, that's what I'm talking about. So, and where this really comes up is we'll be talking, there'll be another function that we're dealing with, and I'll go, oh, this is just a butterfly function. meaning it looks like this. It just may have been shifted so that its asymptotes are somewhere else. Okay, so if you ever hear me say butterfly function, that's what I'm talking about. All right, so there's your rational function. Next one on our list. Exponential functions. So these are the ones where we're taking some number, call it A, and we're raising it to the x power. So now our variable is the exponent, not the base. So these guys are exponential. There are some restrictions on A, though. Anybody remember what they are? What can't A equal?
0.
Okay, so A cannot equal 0. Good. There's some other things A can't be. Oh, it's good we're doing this review, huh? So some things about A. It actually has to be bigger than 0. So we can't have negative bases. We also can't have 0 as a base. But there's one more, and that is that A cannot equal 1. So if A is any positive number other than 1, then it's an exponential function. The reason that we don't include the other base, 1 is really boring. Because if you take 1 to any power, you always get 1, which means it's a constant function. So we already know what those look like. Excuse me, they're a little bit different. 0, we have similar issue. Think about 0 to the x. So you take 0 squared, 0 cubed, 0 to the fourth. You keep getting 0. But an even bigger issue is, what if x is negative? Do you remember what negative powers do?
It's irrational.
Yeah, it moves us down. So like if we had, say, 0 to the negative 1. I don't think you can see that up there. So if we did, say, 0 to the negative 1, this would be 1 over 0 to the first, which is 1 over 0, which is bad. That's not just a frowny face, it's a little scowly face because you can't do it. So 0 is definitely a problem, so we don't let it be a base. And then negatives are an issue because of something like, let's say we negative 1 to the 1/2. What's a 1/2 power? What is that also known as?
Root.
Yeah, so that'd be the square root of negative 1.
Or just be imaginary.
Yeah, which then is I, which doesn't give us a scowly face, but gives us a more of a face, right? So this is why we eliminate 0 and negatives. And then again, 1 is eliminated because it's just boring. All right, so exponential functions, as long as A is not 0 or a negative or 1, we got something that looks like this. So what these look like, let me give you an example. There's an example of an exponential. Looks something like that. So let's kind of go through our list of things that we know about it. In terms of its domain, the domain is all real numbers. Plug anything you want in. In terms of the range, it's 0 to infinity. But this 0 is not included. We never actually reach 0, but we get as close as we want. Okay, so we got our domain and range. In terms of intercepts, the y-intercept is always 0, 1. That guy right there, always 0, 1, because any number raised to the 0 power is equal to 1. And then there are no x-intercepts. So how about this guy? Is this one even or odd or neither?
Not even, not odd.
Okay, so it's, yep, it's neither one, because even, remember, needs symmetry, reflective symmetry, which we don't have. Odd would mean we'd have the rotational symmetry, which we don't have. So this one's neither even nor odd. And then the other thing we've talked about, increasing and decreasing. Notice that this one is increasing. However, not all exponential functions are increasing. Some of them are decreasing. It's also possible to have an exponential function that does something like this. It all depends on the base. And like so many things, that case, there is a location in amount that changes whether it increases or decreases. And in this case, this is when a is less than 1. I'm going to greater than 0 because we already know that it has to be that way. So if your base is between 0 and 1, it's decreasing. It's increasing if that base is greater than 1. So the increasing or decreasing depends on that A, just like we've seen with lots of other things. All right, so again, know your general shape of an exponential. How steep it is versus how flat depends on A. The further A gets from 1 on either of these, whether it's an increasing or a decreasing, the further it gets from 1, the flatter it is by the x-axis, and the steeper it is as we move away. So if we had a base like a is equal to 10, so 10 to the x grows very quickly, as opposed to 1.1 to the x, it's going to grow very slowly. All right, so there's a little bit about exponential. I think the one other thing that we've talked about that I didn't bring up yet is, remember one-to-one functions? These guys are one-to-one. The rational function was 1-to-1. The square root of x is 1-to-1. Absolute value is not 1-to-1, right? Don't forget about that as well. All right, so there's a little bit about exponential functions. All right, so then one that's definitely related to exponential functions are what we call logarithmic functions. And if we were all together in the classroom, it would have been at this point that I heard some audible groans. Right? Logarithms. Because that's pretty much everybody's experience with logarithms, right? You probably remember having to suffer through them. You may not remember much about them, but you had to deal with these guys. Well, let me remind you a little bit about them and maybe help alleviate some of those groans. So logarithmic functions, we literally write log, but then we put the little a on here. So we've got log base a of x. And what this is the inverse of the exponential a to the x. So do you remember what inverse functions do?
They take you back to the beginning of the original, of the non-inverse.
Yeah, that's a good way of saying it. I like to say they're the return trip. But think about like a function, right? We plug something in, we get something out. The inverse takes that thing that just came out and gives us what we plugged in. So let's just go backwards. Something that you saw probably relatively recently were the inverse trig functions. Like if you came through our sequence, that was the last math class you took was trig. Remember trig, you plug in an angle and you get out a number. And the inverse is you took that number and it told you what angle you started with, right? So it's going backwards. Well, that's what a logarithm does. It does the exponents backwards. So basically it's like saying, here is the answer. Tell me what power we had to put on A to get it, right? With exponentials, you plug in a power and get out a number. Logs, it's taking that number and figuring out what was the power. Okay, so it's just the inverse function of the exponentials. Now, let me come down here for a second. Okay, so here's the deal though. Logs are exponents. I know you don't believe me. That's okay. But they are. They're exactly the same thing. And an analogy that I like to use that doesn't really work for me right now because my wallet is downstairs, is money. Think about money. Can you tell me who's on the front of a $20 bill? I only asked the 20 because that's what ATM spit out.
Jackson?
Okay, good. Yeah, Andrew Jackson. How about an easier one? Who's on the front of the $1 bill? He says easier, and then maybe it's not.
Washington.
Okay, good. That's George Washington. And then most people know the 100 just because of pop culture. Who's on the 100?
Benjamin Franklin.
Benjamin Franklin, right? It's all about the Benjamins. Okay, so you can tell me what's on the 100, you know, who's on the 100, the 20, you know, and the 10 is Alexander Hamilton, made popular again because of the musical. 5 is Lincoln, 50 is Grant, right? So you got the fronts. Okay, so a lot of you knew Benjamin Franklin was the front of the 100. What's on the back of the 100? How about the back of the 20? I guarantee you get them all the time.
The 20 is the White House, I think.
Okay, you are correct, Vale. The back of the 20 is the White House. Back of the 100 is Independence Hall. Back of the 10 is U.S. Treasury Building, right? Like, okay, so the backs have things too, but you guys don't know them. You don't know them, right? But they really are the same. If I were to show you the front of a 20 or the back of a 20, you are going to go, well, yeah, there's still a $20 bill, and I can still go and, you know, get myself a icy cold root beer down at my favorite drinking establishment. And you don't care, right? Well, think of this. Logs and exponents are just the front and back of the same thing. You're used to exponents. That's the face of the bill. Logarithms are just the backside. Okay, so even though they look completely different, they really have the same information. They are just as valuable, just as useful. It's just we're looking at them from a different perspective. So one of the things that I like to do is show you how you can flip it over. Take this logarithm and turn it back into an exponential because sometimes that helps you see what's going on. Anyway, logs are exponents. They really are. They're totally exponentials. They're just going the opposite direction. Well, because of that, all the things we know about exponential functions, there's a corresponding thing with logs. So first, let me show you how we translate from logs to exponents, okay, because this can be useful. So let me give you a log expression. Just go with log base a of x equals y. So again, remember what I told you is that this y, this is really the exponent that we would put on a to get x. So this is equivalent to a to the y equals x. Okay, so these mean the same thing. So those two statements are exactly the same thing. This is the front of the $20 bill. This is the back of a $20 bill. But the $20 bill is, either way, it's still a $20 bill. Same deal here. You write this log expression, you write exponential expression, same thing. They're exactly identical. They mean exactly the same thing. All right, so to convert, it's actually pretty easy. I'm going to go to a different color here. Hopefully you can still see it. But I call this running the hook. This is another Bruce-ism. Can you guys see that okay? I know it's probably a little bit lighter. So it says run the hook. All right. So this was something that I came up with when I was first teaching, when I was back in graduate school, oh, so many years ago. I was watching football while I was grading, which is what I do. I usually have sports on in the background. And the guy on one of the announcers did that whole thing where they draw, on the screen. And he drew a hook pattern, which just looks like this. Right? It looks like a fish hook. And I just went, oh my God, this is how you convert. So check out what you're going to do. If you're in a log, you start at the base and you run a hook. You run out and turn around. Okay, so just run out and turn around. And everything that we run into on this arrow, we take in order when we make the exponential expression. So we started with a, which is the base. The next thing we run into is the y. Well, so that's why we wrote y here. Then we hit the equal sign, and then we hit our x. Always works. Always works. So you start at the base, run out and turn around. This will convert from log to exponent. It also actually works if you want to go from exponent to log. Now this one I didn't come up with. One of my students was then like, hey, look, you can do the same thing here. So if we run this hook, got to angle it just a little bit. We now have log base a of x equals y. So if you have a log expression, sometimes it's easier to turn it into an exponential expression so you can actually answer the question. So for example, suppose I said, tell me what this equals. I want to know what log base 2 of 32 is. So a calculator can do this. But let's run the hook. So let's make this an x because we don't really know what it is. So we'll call that x. If you run the hook to convert it, we start at 2. We run out and turn around. We're going to get 2 to the x equals 32. And if I write like that, if I wrote, okay, answer 2 to the x equals 32, I bet a lot of you already know the answer. What is it?
5.
5.
5, right? 2 to the 5th is equal to 32. So it turns out that log base 2 of 32 equals 5. So what I mean, if you ever hear me say flip it over, right, turn it over, convert to exponential form, this is what I'm talking about. And you notice how useful it is. It makes it so that we can actually figure those things out a little bit easier because we're more comfortable. You're more comfortable in exponential world. And I know this. That's cool, right? I'll just tell you, me personally, logs were that was like the last part of algebra that I actually understood. I remember in high school, I mean, I was a total math nerd, as you can probably imagine, right? And I remember just feeling like, I don't understand logs. And then it just clicked. I think it was something one of my teachers showed me. And finally I got it. But for me, it was my stumbling block too. So I totally understand. So turn them into exponents. Make your life a little bit easier. All right. Well, anyway, so that's how you can convert these things. So in terms of their graphs, they look a lot like exponentials. They just are on their side. So think about this picture right here, right? Notice how it's got a asymptote on the x-axis and it goes through the y-axis at 1. Well, this one has a vertical asymptote at the y-axis and goes through the x-axis at 1. And this is because they're inverses. Inverse functions have this symmetry. They reflect over the line y equal x. So this is what these guys look like. In terms of their domain and range, they're just opposites of the domain and range for exponentials. Another property of inverses, that they swap their domains and ranges. But again, no y-intercept this time. But there is an x-intercept at 1, 0. So with inverse functions, the roles of y and x swap. So that's what we're seeing here. In terms of increase and decreasing, we actually have the exact same scenario as with exponentials. It increases if that base is greater than 1. And it decreases if that base is between 0 and 1. All right, so that's kind of nice that this is pretty much the same as exponential. You just swap the roles of y and x. So domain and range swap, and also the intercept swap. So know the graphs, but more important than that are the log rules. So let me remind you some rules of logarithms. And these suckers are going to make calculus so much easier. Oh my God. Just wait. You're going to love these things when you see them, not this quarter, but next quarter. All right, so the first is that when you plug 1 into a log, you get out 0. So it doesn't matter what the base is, you always get out 0. Now, why is this? Well, this comes from, remember this rule? A to the 0 equals 1. That's exactly what this is. Run the hook on it. So that exponential rule that you know and love, well, maybe not love, but you know it by this point, that's the same corresponding log rule. Another one that's really useful is if you have the exact number that you're putting in at base, that one, you always get 1. So log base 4 of 4 is 1. Log base 1/2 of 1/2 is 1. Doesn't really matter. And again, that comes from the corresponding log rule or exponential rule. A to the first is equal to A. So I'm writing those exponential rules just to help you, well, to help reinforce that logs are exponents. It's the same idea. And so every rule of exponents that you know and love has a corresponding rule of logs. Okay, the next 3 are the big 3. So the first one says if we have multiplication inside of our logs, we can actually split that up as addition of individual logs. So this really comes from the rule of exponents, not a spacer. But remember this one, that when you multiply, exponential extends, you add exponents. That's where this comes from. I'm not proof. If you want to see it sometime, you can hop on office hour and we'll chat about it. But this is the corresponding rule. So then similarly, there's one that has division. Well, we already know that the rule of logs for exponent division is to subtract. Well, that's what we do over here. We subtract the individual logs. And then the last one is, what do we do if we have a power? Well, we get to bring that power out front as a multiple. So these last three will make doing calculus much faster in certain forms. So we're going to run into those a lot. We use improving. We'll get that, review those things because they are kind of handy. So I will tell you, historically, we're also huge. When that's some technology had today, this turns multiplication into adding. Adding's way easier than multiplying, right? Instead of division can subtract and so on. So it definitely sped things up. Nowadays, I can't use that as a justification, but I can definitely use simplifying things when it comes to horrible stuff like calculus. If you do your rule of logs well, you do some calculus much faster than even technology can. Okay, so know your logarithms and you're good to go. Real quick before I step off of logs, I do want to mention that there are two special kinds of logs. If you ever just see plain old log with no number down here, does anybody remember what that means? What that implies?
Base
10.
Yeah, that one's base 10. So that's common log. So if you just see log, that's 10. The other one is ln. I always make it a curvy L so people don't think I'm writing n, but this is ln. That's the natural log. And that one's where our base is e, and e is that's an irrational transcendental number. That's 2.71828 ... It's kind of like pi. You guys know pi. This is another number like that. It's probably actually pi, honestly, from a standpoint. It doesn't get the love that pi gets, but it's similar to 2.71828, blah, 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 blah. It goes on forever. So if you ever see those, that's what we're talking about. I'm going to just tell you right now, and I'm going to apologize for this. But even though I apologize, it's not enough for me to change what I do. You will often hear me say log when I'm talking about natural log. Okay, so if I write this, instead of saying natural log of x, I'll say log x. Because of the aforementioned laziness on part. Also, mathematically, we only ever deal with natural log. All the other logs, you turn them into natural logs to do stuff with them. And so in terms of the math world, there really is just one log, and it is the natural log. In fact, some calculators only have natural log because you don't need the other one. Anyway, just be ready for those. All right, so the last little bit that we need to kind of review from pre-calc are the trig functions. That's the other set of functions that we've got. And so just want to remind you, there are 6 of them, right? There's sine of x, cosine of x. We also have tangent and cotangent. And then we've got secant and cosecant. So depending upon who taught you trig, where you saw it, you can either develop these by looking at sides of triangles. You may remember things like SOHCAHTOA. It's a ratios of sides of triangle. Or you may have seen these developed using unit circle, looking at coordinates of points on the unit circle, where sine is given by the y coordinate and cosine is given by the x coordinate, and then so on and so forth. But we really have these 6 trig functions. In terms of domain and range and all of that, it really depends which one I'm talking about. Sine and cosine, the nice thing about these is that both of them, the domain is all real numbers, and the range is all the numbers between -1 and 1. You may remember the graphs of sine and cosine. They look like waves. We call them sine waves or sine graphs. These look also identical. The only difference is they've shifted a little bit. Right? They've been shifted by pi over 2. All right, anyway, so those, you should know the graphs of sine and cosine. So let me just show you this, Rick. While I'm doing this, I'm just going to let you know that I will never, ever in this class talk about degrees. Ever. We'll only do radians. Okay, so if you are not comfortable with radians, you will get comfortable with radians, because in calculus, we only use radians. For those of you who took trig with me, you're used to this. I'm actually like a huge proponent of radians. I think we should use them in everyday life. Like, I can't wait for the Olympics when someone's like, oh my God, he hit a 6 pi. Right? Like, that's going to be awesome. That'd be a 1080 for those of you who know quite so over with radians. But it's definitely a pipe dream of mine. I know this. I'm also a huge fan of metric. I don't expect these to come out dating soon, but I'm going to push in the ways that I can. So we're going to only use radians, because in calculus, if you use degrees, everything is harder, way harder, horrible, ugly, nasty. In radians, everything's nice and sweet. Okay, so only radians, 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 radians. Anyway, so the graphs of sine and cosine, I'm going to cosine, because it is my favorite. You all have your own favorite trig function, I'm sure. My sine. And kind of look something like this. And you just look at one cycle of it. I'll put on some coordinates here. The important values are all the half pi's. So from 0 to half pi, to 2 pi. And we get an important point at each one of those. For cosine, there's a maximum at 0, a minimum at pi, another max at 2 pi, and then in between are the x-intercepts. Right, so this is what cosine looks like. It does continue on forever. So you can see the domain is the range. It is trapped between plus and -1. And it just keeps oscillating and repeating forever, right? That repetition, the length of the repetition is what we call the period. And for sine and cosine, the period is 2 pi. That's how long it takes for it to repeat. If you were to draw the graph of sine, it looks exactly the same. You just shift it over. So this maximum is actually at pi over 2. So it comes up through the origin and so on. So cosine is an even function. You see the symmetry. Sine is actually an odd function. What's cool about the trig function is each one of them is either even or odd. So I'll put them over here on the side. Cosine is even, sine is odd. All right, anyway, so that's kind of the important thing about the graphs of those. The other ones, their graphs are interesting-ish, but I don't expect that you know any of them. The only one that sometimes comes up is tangent. And let me go ahead and just give you a graph of tangent real quick. Tangent's one of those that has asymptotes every once in a while. And in between the asymptotes, there's a, I don't know what all this actually looks like that. This tangent. In terms of the important points here, that's pi over 2, pi, 3 pi over 2. Pi, and so on. So it's got asymptotes at all the half pi's, and then intercepts at the whole pi's. So that's what tangent looks like. Cotangent, similar, it's shifted, but it's not a reflection. Because of alternating smiles and frowns, kind of. I'm not going to list out domains and ranges for that, but I do want to mention that the periods for tangent, cotangent are actually pi. They repeat half the time. For their periods are also 2 pi. In terms of even and odd, the only other one that's even secant. All the rest are odd. So just so you know the information. All right, so for Bruceage, just so you know, the ones above kind of blue squiggly line, sine, cosine, and tangent, I call these the big three. Because they're really the only ones you need to know. They're the ones your calculator knows, calculators know. So I call those the big three. If you ever hear me talk about big three, it's sine, so the other big thing that I want you to remember, at least I've done in trig, that's going to matter for later, are the identities. So let me really quickly remind you of a couple of identities. And these are ones that you're going to use a lot. Okay, first are the reciprocal identities. These you find the other three, where cotangent is 1 over tangent, secant is 1 over cosine, and cosecant is 1 over sine. Those you'd know, just flat out know. So know how to get to the big three from the other three. Another one you should just know is that tangent is equal to sine over cosine. Because in actuality, you don't need to know all of the big three. You only need to know sine and cosine. If you know sine and cosine, you can get all of the rest. Okay, so those should just be not ones you have to research or anything, you just know them. There is one more that you probably know that you don't have to research, and that's the one we call the Pythagorean identity. And it's one that goes sine squared plus cosine squared equals 1. Sine squared plus cosine squared is equal to 1. Uh-oh. So my audio is glitching. Let me try something here.
Only for like the last couple minutes.
All right, that might be just my internet getting slow. Luckily, we're about wrapped up. Let me just show you 2 more identities real fast that are going to be useful. So there's another one that's related to this. That's tangent squared plus 1 equals secant squared. You may not know that, but this one will come in handy, and it's related to that guy. Another one that I want you to kind of remember about is the double angle identity for sine. Looks like this. And there's a similar one for cosine of 2x. And it looks like cosine squared minus sine squared. But I'm going to do you a favor. I'm going to upload onto Canvas an identity sheet that has all of the trig identities, just so you got it for your reference. For the most part, I don't expect that you have them memorized like these guys, but they are going to come handy when it comes time to doing calculus. All right, let me come on down here again. All right, so there was your year of pre-calculus in like 3 hours. Obviously, we flew through, we just sort of hit the highlights, but I tried to concentrate on the things that are going to be big for us going forward. So what we're going to do on Friday, next class period, is we're actually going to start the calculus. We can talk about what calculus is, like questions it was created to answer. All right, so I'll give you a little historical context, and then we'll start working on the tools for actually doing it. All right, so I'm going to pause the recording here.